Now that we've done an example of solving a linear programming problem, let's work on an applied problem and see if we can put this into practice and find an optimal solution. So the next example in the packet is on diet formulation. Let's go ahead and read it through and try to see what we know. So it says a diet is to contain at least 16 units of carbohydrates and 20 units of protein. Food A contains 2 units of carbohydrates and 4 of protein, while food B contains 2 units of carbs and 1 unit of protein. If food A costs $1.20 per unit and food B costs 80 cents per unit, how many units of each food should be purchased to minimize cost, and what is the minimum cost? So it appears as though we have two food options. Obviously, in a real problem, we'd probably have way more than that, but in order to keep it solvable, we'll keep the situation relatively simple, where food A is much more dense in protein, food B is more dense in carbohydrate, and certain food, food B is a little cheaper, food A is a little more expensive. And we want to have a little bit of a balance of both foods in order to get the desired amount in our daily for our daily nutritional needs. And also at the same time, we want to make sure to minimize cost. So we have a series of constraints, and really the constraints are what are listed above, basically that we need to have at least 16 units of carbs and 20 units of protein. So as I read those, I'm kind of thinking to myself, these are an inequality. And when I'm looking at food A and food B containing certain amounts, we know that each of those, when combined, would contribute to the carbohydrates and the protein, and those could be used to write inequalities. Additionally, we have another statement that food A costs $1.20 and food B costs 80 cents per unit, and that would factor into the cost. So since that's what we're trying to minimize, that's going to be our function. So we could go ahead and write that right off the bat. And also, it's probably smart before we start writing equations and inequalities to write down our variables. What is it we're trying to solve? And what we're trying to solve is how many units of each food, whoops, that's the eraser, how many units of each food should be purchased. And let's go ahead and just call those A and B, because A is the amount of units of food A, and same for B. Go ahead and note what everything stands for. But also notice there's another thing that another unknown is that the amount of carbohydrates and the amount of protein that we have. So let's go ahead and call X the units of carbohydrate in our diet and Y the units of protein. And those things are related to each other, but those also factor into things that we don't know. And one thing that we know is that X has to be at least greater than or equal to 16, and Y has to be greater than or equal to 20. As the original first statement says, the amount of carbs in our diet has to be more than 16, and the amount of protein has to be more than or equal to 20. And at least always implies that it could be exactly 16 and 20. That is totally fine. But another equation that we could write, so that those would be all the variables that I could think of to start with. But another thing is the cost. What we're trying to minimize, and this is kind of like there's one function that we're trying to solve, and this is always going to be the isoprofit line that we're trying to look for is going to be like in the last example it was profit. We're trying to minimize or maximize profit because we want to make as much money as we can. But if we're looking at the cost to our business, or in this case of our diet, if we're a nutritionist or whatever, we often might want to spend less money, so we're trying to minimize cost. But in this case, it says that it's going to cost $1.20 per unit of food A and 80 cents per unit of food B. And since I used A and B to describe the amount of food for each of those, our cost function is going to depend on how much food A we buy and how much food B we buy. And after all is said and done, that's what our goal is to figure out, well, what is A, what is B? That way we can finish finding what the cost would be. So if I'm thinking about starting a graph, And looking at our feasible region, A and B could, one thing I could think about is, what am I going to use this X and Y on my graph for this A and B? And that's something which is not always going to be obvious. When I was looking at this question for the first time, it took me a minute to really figure out which variables I wanted to deal with. But since my cost function is based on A and B, and since that's what I want to find, I'm confident that A and B are the choice of variables that we want to solve for, not X and Y. Because it doesn't ask us, how many units of carbs and protein are we going to get in our diet. That's not the question, so I'm not solving for X and Y. But you could call these X and Y if you want. But there's a lot of unknowns, which is why this question is a little bit harder, in my opinion. But anyways, from here, the last piece of information that I have not noted is the statement that food A contains 2 units of carbs and 4 of protein, and food B contains 2 units of carbs and 1 of protein. And my goal is to use these constraints to try to write an equation in terms of A and B. The issue is those constraints are not going to match up with the units on my axes, right? Because I chose to use A and B as my graph, and those are what I'm trying to solve for with respect to my cost equation. And these are not going to be in agreement with A and B, so this is an initial problem I have. But in reading the second and third sentence, food A contains 2 units of carbs and 4 of protein. And what I could look at is how much carbs each of the foods have. And because obviously, if I'm going to buy that food, those are all going to be joined in my diet. And basically, however much A I buy is going to contribute to 2 units of carbs, and however much B I buy is also going to contribute to 2. So I could write that as an equation as 2A plus 2B, and this will give me the amount of carbs I have in my diet, right? Because that's what X is how many units of carbs I need. And for each unit of A, I'm going to get 2 carbs, and for each unit of B, I'm going to get 2 carbs. And then the second part of that is the amount of protein in each of these foods, whereas food A has 4 units of protein, so each A I buy in the very same way. Let me make that cleaner. My thing is messed up. I don't know what's going on. My window size is messed up, and I'm gonna refresh. Hopefully not have to redo this whole thing. Okay, sorry, technical difficulties. So it's because when I double clicked in my tablet, for some reason, all the menus zoomed in, I couldn't see them anymore. Okay, sorry, back to where I need to be. So going back to this question, we had food A contained 4 units of protein. It's protein heavy. Food B, only 1, less protein. So, and again, since I'm buying all that for my diet, I know that for each A that I buy, I'm going to get 4 units of protein. And when I add that to B, B only contains 1 unit of protein. And when I add all that together, that's going to give me the net protein in my diet. So I could kind of think of these equations as, well, this is how much carbs I'm going to get in total, and this is how much protein I'm going to get in total. But the last thing that I also know is that I need at least 16 units of carb in my diet, and I need at least 20 units of protein. So X must be greater than or equal to 16, which implies this also must be greater than or equal to 16. And Y must be greater than or equal to 20, which implies that for A plus B must be greater than or equal to 20. And this is the important thing that we needed to know. We needed to find the constraint inequalities, which were not necessarily obvious. And in a word problem, it's something where you're often going to have to read through the problem to try to see, figure it out, reading comprehension and all that. So like any word problem, I'm trying to give you some tips about how I would figure it out. And this one, when I first tried it, the equations that I wrote were just wrong, and so I got kind of stuck for a minute until I really thought about the equations that I wrote, and I recognize that, okay, these actually don't make any sense. And so, if you do get stuck on word problems, that's very, very normal. It happens to everyone. So anyways, now we have everything we need to know. We have the constraint equations, and we have the cost equation. And our goal is to minimize cost. But basically now I want to build my graph as we did in the previous example. So I have that 2a plus 2b is greater than or equal to 16. So I want to graph the boundary equation. So the intercepts for this will be 8, 0, and 0, 8. So another way of graphing lines that I tend to use quite often, especially in these types of equations, is finding the x and y intercepts. So like looking at this equation, and the easy way to do that is to plug in 0 for a and b. So if I plug in 0 for a, b must be 8 to create equality. And if I plug in 0 for a, b must be 8 because, well, they're both 2. And 2 times 8 makes 16. So what I end up with is 8, 0 and 0, 8 as two of the intercepts for these particular equations. So I'll go ahead and graph those, 8 and 8 on each axis. And this will be the first line of the inequality. And also note that it's an equals, so the boundary line should be solid. And since it's greater than or equal to 16, it should be shaded up, but it's not. You can't necessarily tell just by the sign of the inequality. But if I were to solve it for b, it would be b is greater than. So it should be the b direction shaded up. So really, it should, be shaded upwards above the line. Since I need to have it more than that, I don't want to have less than the desired amount of nutrients. I want to have more. And in a lot of the other examples, we were always shading down. But that usually when you're trying to maximize something, you shade down. When you're trying to minimize something, you shade up. Though again, it's not necessarily that simple, but that's fairly typical. And then for the second equation here, we would have that if I plug in 0 for a, b would be equal to 20. So that would be my y-intercept, and that's going to be a little bit not perfect on my graph, but b is equal to 20 would be way up here. And then if I plug in 0 for b, a should be equal to 5. So this line is going to have quite a bit of a steeper slope to it. Come down here at 5 and should look something like that. Again, this is a rough sketch. It doesn't need to be perfect. It just needs to be good enough so that I can solve it. And basically, it needs to exceed each of those. And technically, I could have like 1,000,000 grams or units of carbs and 1,000,000 units of protein. But obviously, usually when we're dieting, we want to have as close as possible to the desired amount. But the more of that I buy, the higher the cost will be. So as I'm looking at the graph, the values, going this way are all technically part of my situation. What I get is an unbounded region. So our feasible region here is not bounded like it has been typically. It's technically going to infinity. But since we're trying to minimize cost, the minimal cost is probably going to be on the lower side of the boundary line because we're buying less of that stuff. And basically, as we discussed before, the minimal solution should be on the corner point. So if I'm looking at this, basically I can tell I have the lower side of this region looks like that, and I get 3 corner points. And if I want to figure out which is the best, I could check each of those corner points to see which one has a minimum cost in the original formula. Also, notice when I'm graphing something like this, I don't necessarily know what the corner point is. And this is kind of another thing I wanted to address is how do you solve these point of intersection or the corner point? But basically, the point where those two lines overlap is a solution to the system of equations as opposed to the system of inequalities. Because I got those two lines, where they overlap is where the system intertwines. So really, I need to solve this system removing the inequality signs, and the overlapping point would be the answer. And well, we talked about various different ways of doing this, like you could just use your calculator. But let's go ahead and use our chapter 6 theory to solve this. So we could type this in as a matrix and use the RREF, the reduced row echelon form, to find where is the overlapping point and basically get algebraically that corner point. So I'll go ahead and type my matrix in my calculator, which should have coefficients 2, 2, 16, 4, 1, 20. And if I quit, I could go to matrix math, RREF matrix A, and this should solve my system for me. And it turns out that A will be equal to 4 and B will be equal to 4 as this overlapping point. So basically this point right here is 4, 4. Actually, let's use another color because it is hard to see. Something weird is going on. I don't know what, but this point right here is going to be 4, 4. And this point right here will be 8, 0, as previously found. And this one, oops, not that one. Don't care about that one. Care about this one, which is 0, 20. And anyways, what I now want to do is plug each of those into my original cost function and find which one is the minimum cost. So as sort of a summary here, every point within the feasible region would satisfy the conditions. It would give me more than enough carbs and more than enough protein. Anything down below here is going to be shortchanged either on the protein or on the carbs or both. Since I'm trying to minimize costs, it should be along one of those boundary lines. And I'm not really sure which until I try. Often it's going to come right along the point of intersection, but it could go either way. It really just depends on the slope of the cost equation. But neither one of those is very extreme. So without doing any work, my guess is it will be the 0.4, 4, but we still need to check to make sure. And so to finish that up, we're going to plug those 3 points into our cost equation and see what happens. So in the cost equation, we would get that, well, it's $1.20 per the amount of A I bought. So let's start with, I guess, 0.0, 20. At that point, suggests that I'm going to buy 0 of A, and I'm going to buy 20 units of B. And the cost to do that would be, well, 0.8 times 20 is 16. And so I guess $16 would be my daily cost of buying 20 units of food B. Or I don't know if it's daily or whatever. I don't think the question even specifies. But I need to check the other points. So if I were to buy 4 units of each food A and B, that sounds a little more efficient than buying 0 and 20 without doing any math. Whoops. That would be 4 units of A and 4 units of food. Which would be 4.8 plus 3.6. Or no, sorry, 3.2. 8 times 4 is 32, not 36. Which would be exactly $8. And then I could check the cost of the third corner point, 8, 0. So that would suggest that I'm going to buy 8 units of the first food and 0 units of the second food. And the cost of that, since it's $1.20 per unit of food A, would be 1.2 times 8, which should be 4.8 times 2 is 9.6, $9.60, which, since my goal was to minimize cost, it appears as though the solution 4, 4 was my optimal answer as my guess. But again, it could be any point. It just depends on the cost equation, and we just got to check each one in the cost formula. And so summary and conclusion here, we want to buy 4 units of the first type of food, and geez, my hair's out of control, and 4 units of the second food. And if we do that, it should cost us $8, and it should give us exactly the amount of dietary food we need. Because that will, in each food, food A provided 2 units of carbs, and food B provided 2 units of carbs. So if I buy 4 of each, that would be 8 plus 8 is 16, and that would satisfy my requirement to have at least 16. And if I buy 4 units of food A and 4 units of food B, that would give me, since A had 4 units of protein per unit of A, that would be 16 protein for the 4 units of A, and 4 units of protein for the 4 units of B, adding up to 20 units of protein, which is exactly what we wanted as well. So there we have it. This one was quite a tricky one, and hopefully that made sense. And I remind you that the general strategy for solving these types of problems in your homework is to try to write the equations. So try to find the constraint equations, try to find the cost equations. Do your best. If you get stuck, come ask me for help. Ask a tutor, ask a friend, see what you can do. But ultimately is to find the inequalities, graph the inequalities, find the points at the edges, plug them into the cost equation or profit or whatever it is you're trying to minimize, maximize. You don't use that in the graph. You put those corner points into the formula. And after we weigh those options, we can figure out which one is either the minimum or the maximum. If I wanted to maximize cost, well, technically these wouldn't make any sense because I could just buy 1,000,000 units of A and B. So usually the question should have a sensible solution to it, and it, in the case of a region which is not bounded like this one. That will wrap up this section. In the next video, I'll talk a little bit about when you could have multiple solutions and what that looks like and when that could happen. And that will wrap up lecture for this week. Next week, we will be working more on Chapter 7 and continuing on with some of these ideas. And these are ideas that are they're not exactly standard concepts in algebra or whatever. So a lot of this stuff is probably very new, and I recommend that you practice these and try to work pretty hard so that, when it comes time to the final, you're prepared and you kind of know how to progress through these types of problems. Anyways, see you all next time.